All right, good afternoon. This is 3-3. Proving lines are parallel. Now you'll notice on your notes, kind of made the mistake again of having it all filled out, but that's okay. For this one, it actually works out a little bit better since I'm not there with you. So if we'll just start, I'm just going to go kind of quick through it. We can fill in some more questions when I get back tomorrow, but I just wanted to do a quick update. So proving lines are parallel, 3-3. If two coplanar lines are cut by a transversal, so there's two coplanar, so that the pair of corresponding angles are congruent, then the two lines are parallel. So this is the converse of the corresponding angles postulate. So the corresponding angles postulate was that if these two were parallel and they were cut by a transversal, these two corresponding angles were congruent. So the converse of that, if they are congruent, then the two lines are parallel. So that's how we can prove that two lines are parallel, is show them being cut by a transversal, and that congruence is proved from those corresponding angles. Now, technically, you can use other angle pairs to prove that they're congruent, but corresponding just happens to be the one for this one. So using the converse of the corresponding angles postulate and given information, show that line L is parallel to line M. We're given that angle 4 is congruent to angle 8. So that's something that is known to us. Say somebody measured it and it happened to be congruent. The angles were equal. So we know that. Somebody told us that. We can then directly apply, because those are corresponding angles, 4 and 8 are corresponding angles, we can use the converse of the corresponding angles postulate to prove that L is parallel to M, because that is the transversal that cuts them. If those two are congruent, then they are parallel. Okay. Now we can use that with, and now we have some angle measures. We're going to prove that they are this way. So we're given that measure of angle 3 is 4x minus 80. The measure of angle 7 is 3x minus 50. X itself is 30 degrees. Okay, that's all information we know. Okay, so that's our reason number 1 is given. Okay, using the substitution property of equality, I can plug the x, the 30 in for my x's. 4 times 30 is 120. 120 minus 80 is 40. 3 times 30 is 90. Minus 50 is 40. That's just the reasoning behind that is simplify. I'm going to continue the proof on the next slide. So the measure of angle 3 equals the measure of angle 7, right? Remember, they were both 40 degrees. Okay, that's just the substitution property of equality. We take measure of angle 3 equals 40 degrees, measure of angle 7 equals 40 degrees. We plug in the measure of angle 7 in for the measure of angle that 40 degrees. Okay, using the definition of congruence, right? Remember, with measures, we say they're equal. With the actual angle names, we say they are congruent. So this is the definition of congruent angles. Just saying if their measures are equal, then the angles themselves are congruent. So that's reasoning for number 5. And then for number 6, we know that these two lines L and M are parallel, right? 3 and 7 are these two, because those are corresponding angles, right? 3 is corresponding to 7. If they are congruent, then the lines are parallel. So that is the converse of the corresponding angles postulate. Okay, so that takes us through that second example. So we do have some other parallel line postulates. Like I said, we can use other angle relationships. And these are all the same angle relationships that we talked about with our transversals. The only difference is we're given the angles, we're told that the angles are congruent, and then we do the converse. So if a angle is congruent, then the lines are parallel. So on the regular ones, So on these, if you said on the conditional statement from the original alternate interior angle theorem, it was if you have two parallel lines cut by a transversal, the alternate interior angles are congruent. This one is if two lines are cut by a transversal so that the alternate interiors are congruent, then we know that M and N are parallel. So it's just backwards. And that's what the converse is. Remember from our last chapter, chapter 2, that is the definition of the converse. It was the conditional is if P then Q. Well, the converse is if Q then P. So in this case, our Q is the if they are congruent, and the P would be then they're parallel. The converse of the alternate exterior angle theorem, very similar. The only difference is you're proving this because the exterior angles are congruent, not because the alternate interiors are, right? So we know that they're parallel because this alternate exterior relationship. And then the one that's a little bit kind of off, a little bit harder, is the converse of the same side interior angle theorem. It is the same thing if they add up to 180 degrees. If these two same side interior angles add up to 180 degrees, that also means we can prove these are parallel. Now that one I would say is a little less common. I would probably even make the relationship of use vertical angles and then do alternate interior or something like that before I would resort to the converse of the same side interior angle theorem to prove it, because in the end I would probably prefer that rather than setting them equal to 180, but we can, right? All these angle relationships are true if you are cut by a transversal, if these two lines are parallel. So all of these can be proven if the two lines are parallel, okay, or vice versa. In this case, we're proving that the lines are parallel from any one of these. And again, with a transversal, if these are really parallel, all we need is one angle to find all the rest of the other 8 angles. So really, you're not locked into just one of these. So the proofs that I'm showing you, they're not necessarily the only way that you can go about proving these, right? You can use other properties to find other things and prove it different ways. These are just one way to solve. So let's prove this, that R is parallel to S. So R and S, it looks like they are on this diagram, but we want to prove it. So angle 4 is congruent to angle 8. So those are those two. Now the trick here is you just need to figure out what the relationship between those two angles is. So number one, it's given to us. We know that those are congruent. Somebody went out there and measured it with a protractor and found they were congruent, right? Angle R. So R is parallel to S because of this relationship. Now think to yourself which one it is before I tell you. All right, this is the alternate exterior angles, right? These are alternate exterior angles. So the reason that we know these are parallel is not the alternate exterior angles theorem or postulate. It is the converse of the alternate exterior angles theorem. All right, let's keep going. So again, we've got some numbers here. Now, it looks a lot more complicated than it is. They give us what X is. So really, this is just sorry, I've got my son showing us his picture. He's doing some drawing. So, yeah. So we got measure of angle 2 is 10x plus 8. Measure of angle 3 is 25x minus 3. X is 5, though. So the first thing is given. We can use the substitution property of equality to plug 5 into both of those and find out what that angle is. So 10 times 5 is 50, plus 8 is 58, so measure of angle 2 is 58. Measure of angle 3, we have 25 times 5 is 125, minus 3, 122. So 58 and 122 for those two angles. That's just simplifying. Now we keep going, and we know that the measures of those angles right, equal those values. So that's just substitution, right? It seems a little unnecessary to do that, but that's technically the steps that we would take. We know that those add up to, so 58 plus 122, we simplify that to equal 180. Now this is the one that I said I probably wouldn't really do that often. I would probably find another one, but for our example here, this is what we're doing. So measure of angle 2 plus the measure of angle 3 is 180 degrees. That is that relationship 2 and 3. They are same side interior, right? Same side interior angles should add to 180 degrees if these lines are parallel. So since they add to 180 degrees, then we can say that these two lines are parallel using the converse of the same side interior angles theorem. Perpendicular lines. So that was it. That was our whole 3-3. There's lots of other options on your homework. You'll get to do some as well. We'll go over it again tomorrow if you need some help. 3-4, perpendicular lines. So perpendicular bisectors of a segment is a line perpendicular to a segment at the segment's midpoint. So perpendicular, okay, meaning it forms a right angle, and then bisector. Remember, bisector means it like cuts it in half. It makes two sectors of equal length. So it's a line perpendicular to a segment at the segment's midpoint. The shortest segment from a point to a line is perpendicular to the line. So if you have a point and you have a line, the very shortest distance is the perpendicular distance. And we'll look at some things. This fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. So that's a lot of words, a lot of let's look at some diagrams and some problems to kind of help shore that up. Yeah, let's check it out. So let's look at this triangle or set of triangles. Name the shortest segment from point A to line BC. So we're trying to find the shortest segment. So it's either AC, AP, or AB. Those are our options. Now, from the diagram, it's pretty obvious to tell. But again, diagrams aren't always to scale. So mathematically, we can use what we just learned, that the perpendicular distance is always going to be the shortest. So this AP line is perpendicular to BC. We know that from this right angle symbol here. So we can say that AP, right, segment AP is, hold on, there we go. Segment AP is our shortest distance, and that distance is 12 units. Okay, it doesn't give us how many, what that is, 12 inches or whatever, 12 units. Then it asks us to write and solve an inequality for x. Now, how we're able to do that is that we know that this length is the shortest. 12 is the absolute shortest that we can be from A to this BC line. So since x is part of this AC line, we know that this AC has to be bigger than 12. So I'm going to write an inequality that says AC, or 8 minus x, or x minus 8, excuse me, what AC is, has to be bigger than my shortest side, than my 12. Okay. Then it's a matter of just getting x by itself. We'll add 8 to both sides, and we get x has to be greater than 20 for AC to be larger than AP. Right, name the shortest segment from point A to BC. So here's A, and we're going to BC again, this line here. Now, we find the right angle, here it is, right? We know that from the little right angle symbol there. And the shortest distance is going to be that. It's that distance right here, the perpendicular. So segment AB is the shortest, and it has a value of x minus 5. Okay, it tells us that right there. Now, let's write and solve an inequality for x. Okay, so I know that this has to be the shortest side. 12 has to be larger than x minus 5. 12 cannot be smaller than x minus 5, or x minus 5 has to be smaller than 12. Right? So we know that x minus 5, so we add 5 to both sides. Oops, maybe I skipped a little bit. Well, we would add 5 to both sides, and we would get x has to be greater than 17. Let's check my paper real quick. I missed that one on my... Yeah, or x has to be less than 17, right? Because it's 17 minus 5 would be 12, so it has to be smaller than that if you're looking at your notes. Let's name the shortest segment from A to BD. So A is right here, BD is this line here. The shortest segment, we find the right angle, this one, and we see that that is 6. Okay, segment AB particularly. So the value of 6. Write and solve an inequality for x. This time x is part of this AC. We know that that has to be larger because A to C still exists on that BD line, right? It's still A to C. Since C is on that BD line, we know that AB has to be shorter than that. So I'm going to say 6 has to be less than x minus 3, or x minus 3 has to be greater than 6. So again, I would just solve for x by adding 3 to both sides. Right, so we get x has to be greater than 9. Okay. Right. So now let's name the shortest segment from, let's see, A to, where am I? On my wrong page. From U, point U here in the middle, to the line. Now it says the line, there's 2 lines on here, so we're going to just look at them both and kind of see which one's the shortest to each line. Now I know the shortest line on here has to be this one, right, UT, because UW is x plus 4. UT is just x, so this is 4 more than UT. But we'll write them both. We know segment UT, because it's perpendicular, has to be the absolute shortest, but UW is the shortest to this line. All right, so if we're looking at line VW, segment UW would be the shortest that way. So let's write and solve an inequality for x. Again, we know that x plus 4, that's this guy right here, has to be less than 21. Right, that's a shorter distance than this one. So I would say minus 4 on both sides, so x has to be less than 17. All right, let's check out a couple more properties, theorems of perpendiculars. So if 2 intersecting lines form a linear pair of congruent angles, so here's 2 lines, line M, line L, they cross and they form a linear pair, right? Then the lines are perpendicular. So if these form a linear pair, then those lines are perpendicular. We also have something called the perpendicular transversal theorem. So in a plane, that just means on some surface, right? If a transversal is perpendicular to one of the parallel lines, so if this transversal Q is perpendicular to N, like it shows here with that right angle, and these 2 lines are parallel, N and P are parallel, then it's perpendicular to the other line, right? And we know that this is an extension of those like alternate angle and corresponding angle theorems that we just talked about, right? We know all of these angles are going to be defined, and so we can use those defined values and defined properties to say every single time that this is a right angle, this is also going to be perpendicular or right angles. And then this last one, 3-4-3, if 2 coplanar lines are perpendicular to the same line, so if these two lines are perpendicular to the same line, then we know these are parallel, right? If these are perpendicular, then we know that they are parallel. So two lines perpendicular to the same line, therefore the two lines are parallel. All right, so let's do some proofs. I know everybody loves proofs, so let's do some. All right, so given a two-column proof, or we're given this transversal setup, we know that R and S are parallel. So right away, we know some alternate angles and corresponding angles are all going to be congruent. We know that angle 1 is congruent to angle 2. Okay, we know that angle 1 is congruent to angle 2. How do we know that R is parallel or is perpendicular, to T? So R and T are perpendicular. Well, we can start off by our given. Okay, so this R is parallel to S, angle 1 is congruent to angle 2. That's all given to us. Okay, done. Reason given. Now we know that angle 2 is congruent to angle 3. How? Angle 2 and angle 3. We know these are parallel, cut by a transversal, so that's the corresponding angles theorem. Right, those are corresponding angles. So angle 3 and angle 2 are corresponding, so we know they're perpendicular, or they are not perpendicular, they are congruent because they're corresponding. We know that angle 1 is congruent to angle 3. How do we know that? Well, we can do a couple different ways. We know that these form a linear pair, right? We know that these form a linear pair, so I can say that. We also can just use substitution, right? 1 is congruent to 2, and 2 is congruent to 3. So that means 1 has to be congruent to 3. I wrote down, we are switching directions. I wrote down definition of a linear pair. I think that sounds cooler, but in the end, it's all the same, right? We can use lots of different reasons to explain things. There's not just one reason to explain it. So substitution would be equally true. And then how do we know that these are perpendicular then? If we know this is a linear pair, that means two intersecting lines form a linear pair. So T intersects with R. Two intersecting lines that form a linear pair of congruent angles. Therefore, the lines are perpendicular. Now, if you had said that 1 is congruent to 3 because of substitution, you would then have to define that that was a linear pair before saying this. So I was able to say that there were two intersecting lines that form a linear pair of congruent angles, therefore the lines are perpendicular, because I defined that it was a linear pair. Right? That was one of the things that I established. You can use the other properties of perpendicular lines here to prove. We could say because these two are parallel and that these two are congruent, we can prove that this is also perpendicular because these are perpendicular. Right, so lots of different ways you can go about these. This is just one way. I kind of wanted a different abstract-y kind of way. So let's do another last one here. Angle EHF is congruent to HFG, so HFG. And we can see those arc marks showing that they are congruent. Okay, we know that FG, so FG right here, is perpendicular to GH. Okay, so we have our given, that's EHF is congruent to HFG, and then our parallel lines EH. So EH is parallel to FG. We know that, right? We have this transversal, okay? HF, that line is a transversal. These are alternate interior angles, and they happen to be congruent. So the converse of the alternate interior angles theorem proves that EH is parallel to FG. Okay, it's also given to us that FG is perpendicular to GH. So FG is perpendicular to GH. So FG and GH are perpendicular. Okay, that's up here. And so how does that prove that EH and GH are perpendicular? Well, we can use the perpendicular transversal theorem. If a transversal, right, if we know that one of our transversals, so this transversal, GH, is perpendicular to two parallel lines, it's going to be perpendicular, or one of our parallel lines, sorry, it's going to be perpendicular to the other parallel line. Okay, so that would be the perpendicular transversal theorem. That is the second one on that little list. Okay, I don't know. Second one right here, perpendicular transversal theorem. Okay, on this list right here. So in your notes, that's how it should be. There are other ways you can go about solving these, like I said. So kind of use your critical thinking. We'll practice some more with these on the homework, and I'll clear up some questions when I get back. But for now, go ahead and work on those assignments, and I'll see you next time.